Welcome to the fourth session, Grids of Biology and Technology. The upcoming couple of lectures focus on the interface between technology, grids, and the amelioration of human living conditions, either reflecting on the current state of the technological intensity and impact on our well-being, or proposing an optimized visionary model for future infrastructure on a regional level, being based on geomathematics. The grids in these lectures embody a web of connections between theoretical approaches and actual implications between humans and machines. Our first speaker is Dr. Shai Gul. Dr. Gul is a researcher in the Department of Applied Mathematics at HIT and a lecturer in the MDS department with the most creative and innovative course, Symmetry and Fractals. His main interests include discrete geometry and computational geometry, especially covering problems related to computational music. Working as part of a research group of mathematicians and engineers from Bar-Ilan University and SCE College, they have even taught a robot to compose. The journey of mathematics, theorems, music, and design make his approach to multidisciplinary teaching groundbreaking. Let's welcome Dr. Gul.
Hello, everybody. I'm Shai Gul. I'm from the Department of Applied Mathematics. I will talk today about a joint work with Professor Reuven Cohen from the Department of Mathematics in Bar-Ilan. I'm usually interested about covering problems. And when I'm talking about covering problems, I'm talking about facilities locations and how to locate different objects in the plane or in space, depends on which field you're talking about. And this is a theoretical approach, how to do it right. Our motivation is, if you take, for example, the United States continental, if you take all the continental airports in the US, you will see that there is the borders, the blue borders, show that it's not uniformly, that people need to go like more than 1,000 k's to the nearest airport. This is problematic. So this is our motivation, and we're trying to solve it such that every citizen would go from his house to a minimal distance to the nearest airport. Okay, so this is called covering problem. Why is it a covering problem? Because we take every cell and we can bound it by a new unit circle or any disk we want. So this gives an approximation to the optimal covering. How all of these ideas are needs to be in the grid convention, because when you say grid, usually I'm talking about lattices. It's the same thing. It's the same definition, but it's coming in different manners when you're talking about math or you're talking about history or whatever. So, like I said, our motivation is the facility location problem, and I took a very famous example. Let's say we have an antenna of cellulars, and we would like to find the minimal range for every station, such that every point in Israel will belong to the range of at least one station. Okay, like you want to be in the desert, for example, in Israel, and you still want to talk in your mobile, and it's okay. So you need to make sure that every point in Israel will be covered. Another option is if you have an area and you want to decide what is the minimal of antenna that you need to cover the place. So there is two versions to this theorem or to this definition. Okay, so when I'm talking about covering, I'm usually talking about collection of sets, which says to cover a set S if S is a subset of the union of Si. This is a few very famous examples of covering a disk. With three circuits, with three disks, or with 4 disks. Every one of these results is not easy to prove. Okay, the case of 5 circles, for example, is a result of very famous mathematician who called van der Waal. Okay, so this is, for example, we talked about a small area, but what are you doing when you have like a very big region? What are you doing in this case? So it turned out that the best things to do it is to take a grid. Okay, so how do you define mathematically a grid? So mathematically, a grid is a linearly independent vector such that the grid generated them by the sums of xi bi. And if you will see it in the image, it looks like that. This is, for example, a square grid. Like every point, you can see its neighbors together. They fulfill a grid, and there is different options to do it. So if you want to cover Australia with antennas of cellular, one of the possibilities is to take a square grid and just say that this is a cover, and in every point in Australia, you can see that there you have you have a range of cellular antennas. But it turns out that it's not the optimal one. And if you are a cellular company, you would like that the number of antennas that you will cover Australia will be minimal. So how do you do that? So it's turned out by Toth and two very famous mathematicians that the best way to do it, if you have a big region, you need to take the hexagonal regular lattice or grid. And why is that? Because you see in the picture below, it's the same as the idea of the bees. The bees, when they're taking their grid or the lattice, they're doing it in a regular hexagon. The reason is that every hexagon have a maximal area, but still have a minimal parameter. And if you want the maximal, the minimal number of antennas to cover Australia, you will do it by hexagons. But the main question is how do you put the net or the grid on Australia such that the number of cellular antennas will be minimal. So that's what we're trying to talk about today. Okay, so when I saw this theorem for the first time, I was amazed. Blaschke is a very famous mathematician in differential geometry and integral geometry, and Toth is one of the Hungarian mathematicians, very famous too, and they gave the following theorem. Okay, it looks frightening, but it's very easy. The theorem says it's very simple thing. Let's say you have a domain, whatever. You don't know what is the domain, but you know the area of it, and you know its perimeter. The theorem says that even that you don't know the domain, you still can know what is the number of unit circles or whatever, or disks that cover the domain. This is really one of the best theorems I saw ever. And it said, I don't know about the domain, I don't know what is omega, but still I can make sure by this number, 2 divided 3 squared 3, doubled by the area, plus 2 divided pi squared 3 of the parameter plus 1, there will be enough circles or enough disks. This is the number of the disks that will cover the domain. This is amazing result. Okay, so it turned out that this result obtained by geometric probabilistic, and it means the idea turned out from the Minkowski sum. The Minkowski sum is kind of a new product that Minkowski decided to define. So when I write A box plus B, I meant the Minkowski sum, and it says take all the elements from an object X and take all the elements from the object A, take all the elements from the object B, and if you take them together to make a plus between them as a vector, you will get the Minkowski sum. For example, here is a very nice example of taking the Minkowski sum of a square and another smaller square if you rotate it in 45 degrees. If you're taking this sum together, you get a new polygon. Okay? And we can see that there is a meaning how you rotate the polygons. Like different rotations can lead to different polygons. Okay, this is example. If you take an hexagon and a square, in the left side you can see a square that is rotated 45 degrees, and in the right side you can see a hexagon with a regular square without rotation, and you can see that there is a different Minkowski sum. The left side have more vertices, for example, than the right side. So the question is, how do I get a Minkowski sum if this result of Toth and Blaschke connected to Minkowski sum? How do I get the minimal area? So the idea of the proof is, it's very involved, but the idea is it's about how do you find a line, or how do you find a line. Everybody knows how to define a line. One of the possibilities is just to take y equal ax plus b. Okay, this is a line. Another option is just to take a parametric equation as vectors. But the third one, and less popular, or you need to know more deep mathematics, is to define a line by the support function. Like you see here in this image, you can see that there is a line that's supporting the line on the rectangle. So the support line is coming from an angle theta, and you have a length p, and you can define a new the support function of this ellipse, for example. Okay. It has a lots of application to this support function. One of them is that you can calculate the parameter of the given domain, or you even can calculate the area of the given domain. Okay, for example. Okay. So this is the idea. That's what we're trying to achieve. We're trying to use the support function such that we will get the grid in the right direction, that a minimal number of polygons in the grid will hit the convex domain or the given domain. When I say convex domain, I just mean that every 2 points can be, if we take a line between them, they will be inside the given domain of the polygon. Okay. So it turned out that if I'm taking the Minkowski sum of omega of the given domain and the hexagon, which is respective to the regular hexagonal lattice, and I rotate it in 180 degrees, it leads to the given to the domain which we need to cover omega. Again, I mean the Minkowski sum. If I take the Minkowski sum, it will lead me the way, will give me the way how I can cover the given domain by hexagons, by hexagonal grid, which will lead to covering of the domain. Okay. The theorem said that every point that in the Minkowski sum have to be in the intersection between of omega, the domain, and the hexagon. Okay. So how do we construct this this proof? First, we take an hexagon. Okay. Then we'll take another shape, the polygon, the given polygon. Okay. And then we need to rotate it in 180 degrees. Okay. And then we can construct the Minkowski sum. Okay, we construct the Minkowski sum. You can see it in a moment. It will be the domain, the orange one. Yes, this one. Okay. So this is the idea of the proof of Toth and Blaschke. So they said, let's take the Minkowski sum. If we take the Minkowski sum and we will divide it by a unit cell, which is the hexagonal regular cell, we will get to the number of hits of the grids in the domain, which will give us a sufficient covering. But this proof there is a little problematic. Not about the proof, you don't know the exact location. You don't know the exact location of the domain. So what we're trying to achieve, that we'll get a more constructive proof. So first one, we can know, it's easy to show that this covering is not optimal of this proof. So we're trying to improve it in a way. The second one, that for a given domain omega, there exists a lattices which gives better covering than the hexagonal regular lattice. So how do we know which lattice to choose? And third one, you just put the in this proof of Blaschke and Toth, you just throw the lattice randomly on the given domain and calculate the number of hits. But if you will put the lattice in an exact place, you will probably can reduce the number of hits. So you can go to the direction of the optimal solution. Okay, so our result is trying to improve this Toth and Blaschke result by defining the rotation, okay, and defining the translations. It turns out in this joint work that we can find the right orientation of the lattice. Lattice I can put in different ways. And if I put it by this equation, when W is the support function or the width of the omega, we can get the right orientation such that the number of hits, or the number of elements in the lattice will be minimal. Okay. A second one, so if we get the orientation, still we need to decide what is the right translation such that the number of hits will be minimal. And we can determine this by taking an algorithm that we adapt an algorithm from geometry. Okay, so the algorithm says something like that. Take a domain which is bounded by the diameter of omega, okay? And for every cell or for every hexagon, we will calculate its respective Minkowski sum, okay? Okay, so it looks something like that. We take all the Minkowski sums, and when we take all the Minkowski sums, we can reach like the hexagon which is in the origin, have different intersection points, different like in this picture, okay? And since the lattice is periodic, we can look only on the hexagon which is on the origin. In this hexagon, there is different intersections, which this intersection is our intersection between different Minkowski sums. And these different Minkowski sums, or different intersection, can give us the one that the desired location of the translation. I mean that you'll take the intersection which contain minimal in the all other domains or all other Minkowski sum, and this domain on this point we will shift the grid such that the grid will sit on this intersection point of minimal. Okay, so this is the result, and this algorithm can be generalized to 3D algorithm. I can do it, I can decide or I can define what is the exact position of a given domain on a grid such that the number of hits is minimal, and I can do it by taking a prism, okay? Taking a prism or hexagonal prism. I don't have to talk about hexagonal grid. I can get another point. I'm not talking just about translation XY. I can talk about XY and rotation theta, and define it in the same way on 3D. I will get an object in 3D. Okay, so in a similar way, I can define the Minkowski sum, okay, in 3D. It's x, y, and theta. And what I can see, okay, you can see in the that I can define the exact position of the net. This is example how to take the continental airports in the US and decide what is the right location for all of them. In this way, we reduce the number of the distance for every citizen from his home to the next nearest airport to 250 k's. Like if it was before, we're talking about like 1100 k's that every citizen have to go to the next to the nearest airport. So this approach is using the hexagonal regular grid, and it can be very helpful in some if you're trying to plan, for example, a city. So thank you very much for everybody. Thank you very much for Nava and Liora. And that's all.
Questions.
Thank you very much. I have just one question for you, if you don't mind. You spoke about several theorems connected to the geometrical grid. In real life, how can you implement these theorems in, for example, industrial processes or, for example, production lines?
So I think it's usually I'm talking about theory, but here I think I can adapt it very easy because I can know which grids are the best ones. And if I know which grids are the best ones, I can probably decide it in industry which grid will give me the optimal for the question that asked. It depends on the parameter. But every grid have its own properties, and I know for mathematics, for example, which grid to use for every domain. Okay, it's not have to be the hexagonal regular grid. It maybe can be a square grid, but you can minimize it by taking the Minkowski sum, for example.
So thank you very, very much, Shai. It has been fascinating.
Okay.
Take care and good afternoon.